Hey folks, and welcome back to the Machine Learning Dojo YouTube channel with me, your host, Dr. Tim Scarf. Now, it's been a little while since we've been on the air for reasons which need not detain us, but today is the latest installment of our paper review calls series, which has been going on for about 18 months. And the series was just only open for people that worked at Microsoft, but now we've opened this up. Now, the whole point of these paper review calls is that I genuinely believe that machine learning is the next generation of software engineering. We're already starting to see so many use cases in the software engineering world which are unlocked by machine learning. And the next generation of software engineering will be a confection of traditional software and machine learning. And it's really, really important to get good at machine learning because it's an entirely different kind of paradigm. It's a new way of thinking. And the best way to get good at machine learning is to read the machine learning literature. And the machine learning literature should be understandable and accessible to everyone. And that's the purpose of these calls. Now, today we have my good friend, Matthew Salvaris. Matthew is a principal data scientist at Microsoft. He's been working there for a few years. And before that, he did a master's and a bachelor's of computer science. And he did his doctorate in computer science at the University of Essex. His thesis title was Visual Protocols and Mental Tasks for Communication Brain-Computer Interfaces, which is really, really cool. He went on to do a postdoc at University of Essex, and he's been at Microsoft for the last sort of 4 years or so. The paper that Matthew's going to talk about today is called The Lottery Ticket Hypothesis, Finding Sparse, Trainable Neural Networks. Now, it came out of MIT by Jonathan Frankle and Michael Carbin. And the thrust of the paper is that it's possible to dramatically prune neural networks and still not only maintain performance, but improve performance. The paper talks about this approach to find so-called winning tickets. And a winning ticket is just a heavily pruned network. So it's a subnetwork inside the original neural network. It's not only dense networks, it works for sophisticated network architectures like convolutional neural networks, for example, and it even works on some of the larger known kind of architectures for doing computer vision. Now, how does this approach work? So people have been pruning neural networks for 20 years. Jan LeCun in 1990, kind of discovered that you can prune neural networks and they still work reasonably well. And one of the cool kind of computational properties about neural networks, I mean, this is described in the software 2.0 worldview, is that you can prune neural networks and they still perform pretty much, they still kind of do the same thing, just not as well. You can even change the precision on the data types of the weights and the networks still seem to do the same thing. This is really interesting when you contrast to original software, because if you start pulling lines of code out of a traditional software program, it doesn't have that level of continuous robustness. It would just break. But the problem is with naive pruning is that the networks, they do suffer quite severely. They no longer perform as well on the test set. They don't generalize as well. They don't train as quickly. They take longer to converge. So what we need to have is an intelligent way of pruning these networks. And it turns out that it's really intuitive. What you do is you train the network and you look at all of the weights that are close to zero. And you just kind of assume that because those weights are close to zero, they're useless. So why don't we prune them? It turns out that you can do this iteratively, and you can remove about 90% of the weights in the neural network. And as long as you maintain the initialization, you can retrain that network and it will converge faster. It will perform better on the test set, so it generalizes better. It's kind of talking about Occam's razor. And not only that, there are some computational properties which are really desirable. It uses less memory for inferencing. It uses less compute. So these winning tickets are incredibly exciting, and I'm going to have this conversation with Matt and dig quite deeply into it. I hope you enjoy today's conversation. As I said, I'm now opening up the paper review course series, so if you want to do one with me, reach out to me on LinkedIn. Let's make this happen. I'm particularly interested in some of the recent advances in NLP, so if you want to talk to me about Vaswani's paper, BERT, Distill-BERT, GPT, the deep speed thing that just came out of Microsoft, any of that stuff, I'm particularly interested in that. Without any further ado, remember to like, comment and subscribe, and I give you Matthew Salvaris.
Here we are. We are here with Matthew Salvaris. And, as I said in the introduction, Matt is an absolute legend. I've been kind of working with Matt for a few years now, and he's very highly thought of at Microsoft. And there's a paper in particular that I think Matt is really, really excited about.
Yeah, thank you very much, Tim. Yeah, no, absolutely. It's been great knowing you and collaborating with you. But yeah, the paper, well, the lottery ticket hypothesis, I think a lot of people know it. It's a very, very interesting paper. I think there has definitely been a lot of work kind of trying to build upon this. It has a very interesting premise and maybe some interesting implications for generally just training neural networks and understanding how we are able to train these massive neural networks to arrive at good generalizable solutions. Obviously, there's a lot of other work in this area, in this space, but definitely kind of lottery ticket hypothesis is kind of one of those that is kind of making strides in that direction.
Okay, fantastic. So I think we all kind of wondered, there's a bit of a dichotomy with, deep learning compared to classical learning. In the past, the models were extremely parsimonious. That's my doorbell, sorry.
No.
So sorry about that. I knew that would happen. It's bloody typical. Yeah, so as I was saying, there's an interesting kind of dichotomy because deep learning came along and the models were extremely over-parameterized, for want of a better word. We all came from the world of classical learning where the models were extremely parsimonious. And I think there was a degree of, I don't know whether we were deluding ourselves, but we thought that these parameters were necessary and sufficient to learn, kind of more information about the domain. And then as time's gone on, we've kind of realized that they are over-parameterized and much of the representational capacity is kind of wasted learning the same thing multiple times. I mean, what do you think about that?
Yeah, no, absolutely. And especially if you kind of in the early days of convolutional neural networks, people used to visualize the various kernels and kind of what maximally activated the various kernels in a network. And if you did it yourself, you were like, okay, I seem to have like the same pattern being repeated n times, or it's the same pattern slightly rotated. And it just gave you an idea of like, okay, this is kind of a lot of redundant information in here. And as well as kind of successes of various methods like drop lock, drop out, again, seem to kind of indicate that we don't necessarily need that full capacity. And I think that the idea of over-parameterization being in neural networks has been around for a while, and it's kind of been known. But I think what was interesting about the lottery ticket hypothesis, it showed how severe that can actually be. So they would take, so in the original paper, they only did it on CFAR and MNIST. So these are quite small data sets. But subsequently, they've done it on data sets like ImageNet. And again, you can prune these networks to kind of like 80% of their total number of weights, let's say, and you still find that their performance doesn't degrade at all. And so that seems to tell you that, well, we're kind of wasting 80% of this capacity that is available in these networks. Now, again, it doesn't necessarily, these kind of directions don't necessarily tell us exactly why this over-parameterization is necessary. There is definitely a lot of other work within this kind of space that seems to say, well, the over-parameterization is a leftover from the fact that we have poor initialization schemes. Better initialization schemes would allow us to be able to kind of overcome this necessary for over-parameterization. And this over-parameterization is, in essence, in the first part, it's kind of like we're making a bet with n number of subnetworks within this network, and we're hoping that one of these n is good enough that we can actually train with stochastic gradient descent or ADAM or other such optimization methods. So, so to say, basically, we're kind of in this space because of the tools that we have. And if we are able to come up with slightly either better optimization methods or better initialization methods, then we wouldn't have to succumb to doing these tricks or use brute force, in essence, to be able to kind of arrive at a good solution. So a more principled way of initializing networks might give us better results. A corollary of that is like, I think batch normalization is one of the things that is used frequently, but there's been, again, a number of papers trying to explain as to why this works.
Well, on that, sorry to cut across you. On that point, there seems to be an interesting dichotomy between some of these let's call them tricks, and some of them seem to be useful inductive priors that help us learn particular types of data, and it might be learning symmetries in the data or different data manifolds, and some of them are tricks that seem to help us with optimization, like batch normalization and residual networks. So because I suppose the promise of deep learning was that it was entirely data driven, and you could just kind of point this algorithm at this large amount of data and magic stuff happens. And increasingly we're learning that we do need to kind of impute useful kind of inductive priors into the architecture.
Yeah, no, absolutely. So exactly to your point is that we do find that there are, in the current architecture that we use, convolutional networks, there are limitations, that they're not rotation invariant. Even some of the normal other properties that we kind of tend to attribute to them, such as translation invariance, doesn't necessarily always hold up under all conditions. And so being able to kind of imbue them with inductive priors allows us to be able to train these networks without that much amount of data. Now, obviously, as you said, if you have a huge amount of data, you use a lot of augmentation, you're able to kind of partially overcome this. But whether this is a good way to proceed or not, again, it's hard to say. But as to your point of using tricks, I think it's because we're kind of having to do two things. We're having to design a network that is able to solve our problem, okay? But we also have to put into it engineering fixes, such as residual connections, such as batch normalization or clever initialization schemes to overcome the suboptimality of maybe the optimization techniques that we're using. So we're, in essence, trying to fight two battles. One is kind of putting enough knowledge into the network, enough inductive bias into the network to be able to learn the problem, but also at the same time being able to think about, okay, how am I going to optimize this and arrive at an optimal solution?
Yeah, that's really interesting, and I suppose that there's a bit of a tug of war going on in the deep learning world as well, because we have these large over-parameterized networks, and stochastic gradient descent, it's always been difficult at the best of times, but there seems to be some truth to the statement that having a high dimensional space allows stochastic gradient descent to work better. And some of these tricks, like residual connections, for example, seem to make the space more convex and make it easier to kind of make it more learnable. And then this lottery ticket thing seems to be about saying, well, inside this solution space, there exists these kind of solution spaces which are lottery tickets. And by starting the optimization with the correct initialization, you kind of put guardrails on the optimization so it goes where you want it to go.
Yeah, no, absolutely, exactly that. Is that you're so the original paper said that you could rewind the network to its original position and go from there. But then subsequent work, Liu et al. In 2019 said basically that, this works for CPAR and MNIST, but when you try it for deeper networks, it doesn't quite work, or bigger data sets such as ImageNet. I think subsequent work by Frankle et al. And others basically showed, like rewinding to the beginning and using iterative magnitude pruning doesn't work. But if you rewind to an earlier point, so it's kind of the network has gone through some optimization and it's reached a stabilization point. After that, the iterative magnitude pruning does work for bigger networks. So to your point, yes, like there does seem to be a point from which you are able to kind of, if you imagine the solution space, have guardrails that guard, how you kind of progress down this loss surface. Then you are able to kind of reach a good enough solution with a much smaller network. Yeah.
Okay. I mean, I suppose one of the things that surprised me is there's a statement at the end of the paper which seemed to allude to the lottery ticket being already trained. And it was almost because I guess the thing that I'm trying to get my head around is I can't understand or build intuition about the regularity that these lottery tickets appear given different random initializations. So in some of the graphs in the paper, and we can pull the paper up, it said it was averaged over 5 runs, and these lottery tickets appear with surprising regularity. But presumably the structure is different. So what's more important, the structure or the initialization?
That's a very tough question, and then there's been lots of work about kind of randomly initializing networks and then working quite well. And I think even by default, I can't remember the paper per se, but they said if you take a randomly initialized convolutional neural network, it already does better than just random guessing if you give it an image. So yes. Even randomly initialized networks do have. So this is the inductive prior, right? You're saying, well, I'm assuming that the features that I see on the top left of the corner of my image is going to be just as important as the kind of bottom right. And so therefore, you're kind of putting in some prior errors into the network. And so therefore, it's kind of taking advantage of that. But the lottery ticket hypothesis in the original paper was mainly looking at images, but I think subsequently they found it in reinforcement learning. I think they've also found it in kind of natural language processing. So these kind of subnetwork ideas isn't just limited to images, although kind of obviously my interest is in computer vision. That's mainly what I kind of look at.
But do you think that if you look in the solution space of all of the different possible winning tickets, is it homogeneous? Is it clustered, or are they just kind of ran? Do you see what I mean? Because the thing that I'm thinking about is you let's say you randomly initialize the weights again, and then you do iterative pruning, and you find a new lottery ticket, and presumably it's just going to be a completely different subnetwork. And as you were just saying in the paper, one of the graphs shows that you can take a winning ticket that was found and then reinitialize it, and then when you train it, it doesn't converge, and it seems to be almost useless, which means that the initialization seems to be more important.
Yeah, again, I wouldn't be able to say like for certain, but like Desai et al. In 2019, I think there's a paper evaluating lottery tickets under distributional shifts, where they kind of looked at lottery tickets for natural language processing. They found that even randomly initialized tickets are strong baselines. So there's definitely something to do with the original network structure itself. Now, as you said, different randomly initialized networks may have different designs, and maybe two designs that look drastically different have very similar performance or arrive at a similar result. Again, it is possible because of the kind of huge dimensionality and all the possible solutions in this space. So I don't think necessarily that the best ticket is always going to look the same. It could have different architectures. It could look different, basically.
I see, but the intuition is that we could use these winning tickets to learn something about neural network architecture design, and when we look at the topology of the tickets, we might be able to learn something from them. But even then, would that bear relation to the type of data? I mean, what's the degree of kind of data overfitting here?
Yeah, so there was a paper by Fair where they basically looked at different data sets for devising lottery tickets. I think they looked at image data, they looked at places 365. So what they found is that, like the lottery tickets that they found on the specific data set were like worked on that data set, but they also found that winning tickets from other data sets transferred transferred between data sets, let's put it that way. They also found that it was independent of the optimization technique. So it worked with SGD, it worked with Atom. So if you found one SGD, it would work with them and Atom and vice versa. Another interesting point is that they found that from larger data sets, the tickets that they found transferred better than the tickets that they found on smaller data sets. So there does seem to be an element of, is the data that we have representative of the domain enough? And this brings up an interesting idea. So there's been a lot of work more recently with using semi-supervised and self-supervised approaches, both in FAIR and Google. So the most recent example is the noisy student, which I think is state of the art at the moment. And that brings combining kind of that semi-supervised, self-supervised approach to the lottery ticket hypothesis brings up something very interesting. And what you said is that you could imagine that you have a huge data set that you're able to sample from, and that you train this network and you get kind of the lottery ticket. And then you think, okay, this lottery ticket is really optimized for doing computer vision. And so therefore we could use this as a common baseline across everything. Now, so far, we haven't seen any papers that have proven that this is true. And also, I've seen on Open Review some papers where it seems to point that if you optimize your lottery ticket on a specific data set, it still performs better than picking a huge data set and using semi-supervised approaches. But as I said, these papers didn't get through peer review, so maybe the jury's still out.
Yeah, it's interesting. I mean, I remember on that 7 myths of machine learning paper, it was talking about the degree of data set overfitting, and you could actually predict for a given model which data set it was trained on. But what you were just saying, though, about the kind of generalization of winning tickets, it kind of made me think of the generalization of adversarial examples, because you can also, as you know, you can learn an adversarial example from one model trained on one data set, and it's surprisingly effective as an adversary on a different model on a different data set. So it's quite interesting. Right. So let's talk a little bit about stochastic gradient descent. I mean, is it a deterministic algorithm?
No, it's definitely a stochastic algorithm.
Well, I suppose the clue's in the name. Yeah. So it's stochastic in the sense that every mini batch is selected at random.
Yeah.
But I suppose even if it wasn't, if it was a deterministic algorithm in the selection, I suppose it could arguably be stochastic in the sense of the way the CPU architecture is designed. There was a wonderful Lex Friedman interview with Jim Keller the other week, and he was talking all about how the Intel architectures are designed, and he was kind of saying that even if you have a piece of deterministic code, it will never run the same. You just don't know. It'll give you the same answer, but it will run differently.
Yes. Yeah, and people have always use when there's programs that are multi-processing, multi-threaded. It's always very hard to kind of produce a deterministic answer without kind of severely hampering their performance. So that's very true. But like to get to your idea of like stochastic gradient descent and how that kind of affect things. There was a recent paper, I think it's still under review, by Frankle et al. And it's called like linear mode connectivity and the lottery ticket hypothesis. And I think the method that is described in it has been used prior, or has been described at least prior, and is the instability analysis. And the idea is that, when you do stochastic gradient descent or mini batch stochastic gradient descent, let's be precise, you are sampling the data at in a particular sequence, okay? And the question is, if you take 2 copies of the network, and you train them through stochastic gradient descent, mini batch stochastic gradient with different data orders, so they use different, and look at kind of which solution they arrive at in this solution space, and then you examine linearly interpolate their weights, and you find how that affects the error along that path. So the instability is the maximum increase in the train or test error across this path. And so therefore, in this paper, what they did is they kind of used this method to basically say, well, lottery tickets or good tickets are stable at the point where we rewind them to. So instead of rewinding them all to the beginning, you rewind them to this kind of stability point, and it all works perfectly. If you rewind them to a point where it's unstable, then obviously the results that you're going to get are suboptimal. I like this idea of being able to kind of evaluate the stability of a network by looking how, if you interpolate the weights, how your error changes. And I like the kind of empirical. So one of the so in the previous papers where they use kind of like the rewinding protocol, they would say rewind it to epoch k or iteration n. And it was a bit kind of like, well, it's kind of hard to determine this, and obviously iterative magnitude pruning is quite computationally expensive. So being able to kind of say, well, what I'm going to do is I'm going to kind of monitor the stability of the network and use that as a kind of idea of where I should rewind to seems a bit more consistent and a bit nicer approach than just randomly picking a point.
Yeah, so it's really interesting. I love this concept of stability. So why would an over-parameterized network, which was trained independently in the way you say, presumably it would still converge to roughly the same solution space. So why would a parsimonious winning ticket version of that be more stable? Because in a way, it gets at the nub of what this paper is saying, that these winning tickets are more robust, they generalize better, they're more stable, with they're quicker to learn. But why is that?
Yeah, well, that's a good question, and I don't have a full answer for this, but what the stability analysis is looking at is that when you're sampling these mini batches, okay, a part of the information that's contained in there is like the correct gradient to pursue, the correct direction to go in, and part of it is noise, because obviously you're subsampling your data. So what the stability is telling you is that these differences or these erroneous signals that you get from the noise that you get from these mini batches don't affect the final performance of the network. That's what the stability is getting at. So as you said, you were talking about the guardrails and how these guardrails guide you down. Well, it's just basically telling you that you've reached a point where your mini batches, whatever size they are, provide good enough information without getting too perturbed by noise. So it's not like if you imagine you might be on an edge of a surface and kind of the noise would push you off into kind of a ravine. It's basically saying that you're kind of reached a point within the error surface that you're able to kind of progress and not get too affected by the noise in the mini batches, and therefore converge to similar points within the solution space. And so therefore the linear interpolation doesn't increase your test or train error too much.
That makes sense. So that's stability. But what about robustness? Because, again, my intuition is when you have these kind of highly dimensional models, the decision surfaces are actually very, very fine. And if you just perturb them just a tiny bit, you could completely change their performance. What they classify. My intuition is that these winning tickets would still suffer from the same problems with robustness.
Robustness in the sense of adversarial, or robustness in the sense of like our generalization?
Adversarial examples.
Yeah, but the adversarial examples though is kind of hard. I would say I really liked the paper that was in NeurIPS, and it was talking about analyzing the networks in terms of looking at what part of the frequency domain affects them. So very often, lots of adversarial examples are that high frequency domain, and they're the most interesting because that high frequency information is imperceptible to people. So you can't really see this in pictures. We kind of see more of the low frequency information. And what they did in there is they kind of did, if you do various things to kind of guard against adversarial examples, that the standard adversarial examples, which tend to be high frequency, it does tend to hurt your model at performing for kind of low frequency perturbations such as fog, etc. So I would say that the thrust of the paper at the end, though, was saying, look, don't try and guard against adversarial examples per se, but just acquire enough data that your kind of model becomes better. It comes back to your previous argument, what you made right at the beginning, is like if you have inductive priors that allow your network to avoid these issues, then you don't need the data. Otherwise, you need the data and kind of the augmentation to basically get your network to try and be invariant to these perturbations.
Cool. Okay, that makes sense. Towards the end of the paper, it kind of says that these winning tickets might be a necessary and sufficient condition in order to train a larger neural network. Would you agree with that?
Possibly. That's that would be the exciting part, right? Is if that is true, because it means that we, in essence, are able to arrive at architectures that are much, much smaller, that are able to give us better results. And this would be fantastic because, we're currently limited, well, to an extent by the hardware. GPUs only have so much memory. Now, obviously, every year, NVIDIA and others try to produce other devices that allow us to train bigger and bigger networks and come up with clever strategies for doing distributed training, etc. But it would be amazing if we could just simply train really, really big networks on a single GPU. And not have to kind of worry about the capacity of the memory on our devices in order to train these super large networks. Because at the end of the day, this kind of we're like machine learning, especially kind of this area, is very much an experimental driven science. And so therefore the speed of iteration really determines how quickly we can progress. And if we think about it, like there's definitely been a lot of advancements as kind of on the theoretical aspects of machine learning, but a lot of the core central ideas have been around for a long, long time. One of the reasons that we're able to kind of use them in practical applications is due to the fact that we're able to train them within reasonable timeframes and able to experiment and iterate in reasonable timeframes. It isn't that we've kind of made some sort of theoretical breakthrough in understanding stochastic gradient descent or anything else to do with neural networks that's kind of given us this kind of massive explosion in machine learning.
Yeah, I mean, that's really interesting because, as you know, there's this kind of debate going on in the machine learning community at the moment, and it's spearheaded by people like Gary Marcus talking with Jan LeCun and Yoshua Bengio. And, his kind of piece is that there's a real kind of empiricism, as you described, in machine learning. And it's almost quite a dumb science. We're just throwing as much compute and data at the problem. And that's one narrative. And Gary, of course, is saying that we should, move to symbolic methods and introduce memory. But I think that's a slightly cynical method. People like Jeremy Howard are well known for being really, really kind of inventive and resourceful, in how he's won lots of Kaggle competitions just using kind of one GPU and just using his single machine. And I think some of the work, especially from Cohen and Wellen, we had Ilya on the program talking all about some of the new kind of inductive priors to exploit different types of symmetries in the data and different types of manifolds. He was talking about steerable CNNs and gauge equivariant convolutional neural networks and so on. I mean, all of these things to me paint a slightly different picture, that it's not just empiricism. We are actually doing something slightly more intelligent than we were in the past. I don't know. What do you think?
No, I don't disagree at all. And yeah, I think those are very, very good examples. Like especially the gauge equivariant neural networks making things rotationally invariant, I think is hugely important. And obviously Hinton with the capsule networks again is trying to proceed against kind of in that direction. And by all means, these are fantastic improvements and advancements that we've seen in the last year. But for all the success these are in research, I would say that, in the real world, we tend to kind of default to the standard approaches. So that seems to say, there's definitely success there, but it's not enough to dethrone the standard methods that we kind of tend to employ. Now, it could simply be just a matter of time. All these things take time to be adopted. But I think part of it is that there's the unreasonable effectiveness of volume of data and large compute, and I think that's hard to beat.
A quick scan through the paper. So in the intro, I already kind of went through it, but I think some of these figures really tell quite a nice story about what's happening here. So that first figure was talking about because Jan LeCun, even in 1990, he was randomly pruning neural networks, and he kind of noticed that they still work surprisingly well.
Yes.
But when you do randomly prune, of course, they don't converge quickly. The accuracy is not as good.
Yes.
The dotted line on this left figure is the random pruning.
Yes. I would say, so in the past, a standard method for making inference quicker is that you would train your neural network, to convergence. Then you would kind of use some method to prune weights that didn't seem to be important. And then you might do some fine tuning on top of that. And that's kind of a standard way that you would basically get your inference to become quicker. Now, the problem with these networks is that if you did this pruning and you kind of randomly initialize that network, you would find that you couldn't converge to the same accuracy. And that was the big rub. And that's kind of where the lottery ticket kind of changed everything, is that you're saying, no, look, there is a way that you can prune your networks and still be able to kind of get to the kind of same accuracy or same performance, and have a much smaller network. Now, obviously, in the lots of comments, because obviously this was a super popular paper. It got a lot of comments on Twitter. A lot of lots of people were commenting on the ideas, and there's definitely subsequently papers that kind of said, well, the results that you have are great and fantastic, but on deeper networks and data sets such as ImageNet, we're not finding the same thing. And then it was so the kind of iteration on that, the kind of improvement was the fact that you'd say, instead of rewinding it all to the way to the beginning, you rewind it to some point in the training where your network in effect becomes stable. And then from then on, you could use iterative magnitude pruning and arrive at a much smaller network, which you can train from that point. So not right from the beginning, not on randomly initialized weights, but from that point onwards. Now, there has been lots of work that talks about that the training of networks is in 2 phases. So there's like a beginning phase, and then all of a sudden transitions to some other phase. There's lots of different papers that describe this phenomenon. Now, what exactly this means and what does it mean going forward, I really don't know. It would be really great if there was a way that you could say, okay, I'm going to optimize in a reasonable fashion to get to this kind of transition point, and then from that transition point onwards, I can train it much quicker. And so therefore you would be able to kind of, or be able to initialize your network in such a smart way that you're basically in that second part of that training phase. And so therefore your network will converge much quicker and you'll get the results much earlier without having to use a lot of computation. Again, as to what will work, what this may look like, and whether it's even possible, it would be hard to say.
Cool, good stuff. So let's scroll a little bit. So yeah, the algorithm was introduced. So I was saying earlier, the first algorithm is the complete thing where you train and then you prune, and then there was an iterative version created where you can kind of start to prune as after a certain number of training iterations.
Yeah.
So the random initialization, I think that's when you take a winning ticket and then you randomly initialize it.
Yeah.
When then they demonstrated that those random reinitializations didn't work very well, didn't converge.
Yeah.
There's a graph kind of showing this here. So the winning ticket, I think this is the iterative winning ticket, the blue one. This is showing that it still performs incredibly well, even with 1.9% of the weights remaining. It converges very, very quickly. The accuracy is actually better, even in a parsimonious prune state, than the original larger network.
Yeah.
But
Yeah, and definitely kind of, it also shows you that kind of one-shot pruning, it works, but definitely not as good as like the iterative pruning. And that's kind of one of the downsides of the methodology is iterative pruning is quite laborious. Like you remove certain rates, train it to convergence, bring it back, prune certain weights, train it again. And so this iterative process is computationally expensive, and that's kind of one of the main detractions against this methodology. It would be much nicer if you could just do it in a one shot. So you basically train to convergence and then prune the weights and then be able to kind of say, okay, this network is now pruned to 90%. Whereas with iterative pruning, you have to kind of prune a certain magnitude of weights each time in order to get to these very low percent of weights in the network.
Oh, I see. So I actually misunderstood that. So the one shot means you train completely and then you prune once.
Yes.
Oh, I see. I misunderstood. And then the blue one is when you train a little bit and then you prune, you train a bit more, prune, train a bit more, prune, and so on. Yeah. Okay. Yeah, that makes sense.
Yeah. So basically, that's why these steps here look kind of weird, is because these are kind of like how they're determining what at every iteration. I think it is how much they prune by percentage-wise. Okay. And if you think about it, it kind of makes sense because you are training the network, and then once you prune the weights, you kind of removed some of its capacity. So it's not like everything that was in there was completely useless. There's just some, and so therefore the network needs to kind of be fine-tuned in order to kind of again find that you reutilize some of the components that are already in there in order to achieve that capacity, that performance again. And so therefore this iterative pruning allows the network to do that. If you remove too many weights all at once, then it will have a hard time doing it.
I suppose that the thing that springs to mind is, why is this not being used everywhere? Because recently, for example, I think there was a paper about the Lamb optimizer, and it was talking about with some clever tricks and with some special initialization, you can train incredibly large mini batches, and they've been using that to train these BERT models, in record time, and it has far more kind of distributive efficiency than before. I mean, this just seems like such a no-brainer. I mean, why is everyone not doing this?
I think there are two reasons. It's, as I said, it's laborious, this iterative pruning. And then on top of that as well, even though empirically you've proven it for these data sets, you don't know whether it's going to apply to every single domain perfectly. And so therefore, when you're doing these experiments in an academic setting, you want to minimize the number of kind of tricks you're using for your network, because it has unknown consequences. And so maybe in industry, some people are using this method to improve the inference of their models, but also possibly not, because they don't know what the consequences of these are. So that's why.
Well, that's really interesting, because we spoke about Jeremy Howard earlier, and he is the ultimate tricks guy. And
Yes.
as you know, he's got this fast AI library, and he kind of championed things like learning rate annealing and scheduling, and loads of tricks to give you better anytime performance, faster convergence. It seems to me that these graphs demonstrate that doing the iterative approach is actually will converge faster than just training the original network to convergence.
No.
And is that not the case?
No, it's not. It's not.
Oh, okay.
So iterative pruning probably increases your training time by like 5 or 6 times.
Oh, okay.
The only benefit would be is if that lottery ticket, so basically what happens is, like, imagine you're training your network for 20 epochs for convergence. You train it for 20 epochs, then remove a certain percentage of weights, rewind it to the 5th epoch, and train it again. So you're training the network probably 5 or 6 times at least, like what you would normally. So it's actually much more expensive computationally. The benefit is that you hope that you would eventually end up at a ticket that is much smaller. So if you subsequently train the network with more data, you don't have to start with a full network again. You would start with this subnetwork. A. And B is that if you are able to have this subnetwork and fine tune it on other data, that when you put it to be used for inference, you're able to use it to have faster inference. As far as training is concerned, it's always more computationally expensive.
I see. I mean, this seems particularly relevant now, because we've got these large transformers models, and Microsoft have just released this deep speed thing, which it kind of allows you to cursor through memory and be far more efficient, because they've released a model which has billions of parameters in.
Yes.
And the big thing here is if they wanted to release it on the Bing search engine, and I think they are actually doing it, but that's a separate thing.
Exactly.
There are lots of approaches in the literature to making the inference time better on these large models, and this seems like a perfect candidate for that.
Yes, and then the more recent paper, which I don't know who the authors are, I think it's comparing fine-tuning to rewinding. So basically comparing what I mentioned earlier as the point where you train a network to convergence, you remove some of the weights, and you run fine-tuning on that. So you fine-tune the network versus training the network to convergence, rewinding to an earlier point, and like training it again, full. And the results from that, obviously I think it's still under review, so obviously we have to see what other people think about it, seems to say that rewinding does give you better results than fine-tuning. So you're absolutely right. Maybe this methodology would be used in those instances, as you said, where massive amounts, you want to get as inference as quickly as possible. And institutions where it is important that inference is quick and cheap, such as maybe in self-driving cars, or as you said, in large search engines, then maybe methods like this are being used. But again, we don't necessarily see that literature or that information, so it's hard to say.
Okay. Let's have a little scroll. I have a feeling that this one seemed to to show that the random reinitialization failed quicker on the bigger VGG convolutional neural networks. Yes. Because I had this intuition, and maybe it was being brought out by what you were saying about it wasn't reproducible on ImageNet and on some of the larger architectures. But it seems to me that this concept of random initialization and winning tickets seems to become harder on more sophisticated architectures because you have more ducks to line up. And this is kind of what you were saying about, you just need to rewind. You need to start from a fairly good solution before you start the process of finding tickets.
Yeah, and it speaks to what we were saying earlier, and there's a large body of literature on this saying basically the methods that we're using to initialize our networks are not great. We could find better ways of initializing our networks, and that we would still get good convergence for our models. So for deeper architectures, this becomes much more important, just because the possibility of vanishing gradients or exploding gradients just becomes so much bigger as you kind of go deeper within a network. So it stands to reason that they would have a harder time with the deeper networks.
So on page 3, it talks about the implications. So improve training performance, designing better networks, and improving our theoretical understanding of neural networks.
Yes.
So it's talking about the importance of winning ticket initialization.
Yes. And this as I said, there's lots of literature kind of on this domain that initialization of a neural network is hugely important, and that very often we may use techniques to kind of overcome problems with initialization. So I think there's a method called fix-up, which means that you don't have to use batch normalization, and I think it's more commonly used in reinforcement learning. So when you use networks in reinforcement learning, you tend to not use batch normalization because it tends to actually be quite poor. So a lot of people use fix-up to basically initialize their networks in a good way to allow them to converge. So this basically points to this, that these winning tickets are in effect a better initialization method, and therefore allow us to arrive at a good solution with not having a network that's just hugely over-parameterized. Because the over-parameterization allows us to kind of randomly pick a subnetwork that would work and arrive at a good solution.
Okay, cool. And then a little bit down, it talks about the importance of the winning ticket structure. So that this kind of points to Cohen's work, where the winning tickets encode an inductive bias, and the implication of that is that similar effect may be played at the structure of winning tickets, allowing them to learn even when heavily pruned, because it's actually learning something about the nature of the data domain.
Yes, no, you're absolutely right. So the structure of the network is hugely important, and as you mentioned, having networks that have an inductive bias allows us to arrive at good solutions without having to kind of use a large amount of data to be able to kind of find, in essence, we're trying to find this solution via the data, whereas now we're kind of embedding, and with the Cohen's works, we're kind of embedding kind of this prior into our network. Now, obviously, it still remains to be seen. In the past, that's what we were doing a lot of. We were hand creating features. We were spending time heavily manually creating these features. But then subsequently with deep learning, we said, no, let the network kind of figure it all out. I don't sit on either side of the spectrum. I said there's probably a midpoint. Where that is, I don't know. And again, we just have to. That's why it's good to pursue the work in both directions, rather than kind of saying, it's going to definitely be in this direction or that direction, because it's probably going to be a combination of the various approaches rather than just one approach.
Yeah, I mean, and it completely makes sense that we should design models that kind of understand something about, understand obvious things about the nature of the data domain. I mean, for example, if you were modeling human poses, if you took a topological approach, you might model kind of human physiology kinematically, and it would just know that there's a certain range of motion for, the knees are connected to the hips and they can move in a certain way. And if you think about it, you're just making the problem so much more learnable with smaller amounts of data. So it seems kind of intuitive. In the next section, it's kind of talking about Occam's razor. and it's kind of saying that compression and generalization are related, and compact hypotheses can better generalize, and the take-home message is that larger networks might explicitly contain simpler representations.
Yeah, and that stands to reason based on kind of the classical idea of the bias variance. But again, I think this is partially being challenged, especially kind of like the double descent work and the work by Belkin. Now, where again this is going to lead us, I have no idea. I just think it's very exciting that we're kind of seeing these standard ideas being challenged and seeing some empirical work demonstrating that there's, to an extent, these long-held beliefs are not necessarily true, and there might be other dynamics going on in the kind of learning process of these models.
Cool. Yeah, and just to finish off, I mean, the next one's talking about, it kind of shines a light on the role of over-parameterization in neural network training, and we already spoke about whether the presence of a winning ticket is necessary or sufficient for SGD to optimize a neural network to a particular test accuracy.
Yeah, no, you're absolutely right. And, in my mind, I like the fact that we're kind of coming to this conclusion. It's really nice to be able to say, okay, these huge networks aren't absolutely necessary in order for us to arrive at a solution, just because we see a lot of redundancy in them. It would be much nicer to be able to say, okay, we can have a much smaller network that we can train much quicker and get like similar performance, because it means that we would be able to explore a larger domain with the kind of hardware that we have, rather than being limited by what we're able to kind of fit on our GPUs.
That makes sense. And what do you think is the kind of core limitation with SGD now? I mean, because as you said, we need to have the guardrails, we need to have the initialization, but what would it take to have a new improved optimization algorithm that would just work if we could automatically find a winning ticket structure?
Yeah, it's hard to say. And I based on the papers that I read, I always vacillate between different ideas. I really, like, to an extent, I don't know if we're going to ever achieve optimization techniques that are going to be perfect for training these over-parameterized networks. I really like the idea of inductive priors or inductive bias, and the idea of being able to have an initialization technique that's a bit better for being able to arrive at a solution, rather than basically saying we're going to use all these various tricks to be able to allow the network to converge with the kind of optimization techniques that we have currently.
Cool. And just to sort of finish off, what excites you at the moment? What are you most excited about in the domain of deep learning over the next year or so?
A lot, really. So I love free ticket hypothesis, double descent. I really like both of those ideas from the kind of core ML. Again, the inductive bias, inductive priors with Gaussian covariant neural networks, and like capsule networks. I really like the idea of capsule networks. It would be really nice if it came true. It just feels such a nice idea, but again, they seem to have limitations in being able to kind of scale the methodology up. So those are the kind of things that really, really excite me in kind of this domain.
Amazing. Well, Matt, this has been an absolute pleasure. It's an honor, actually. Thank you so much for spending the last hour or so with me. And also, it's been a pleasure working with you at Microsoft. So very, very best wishes. And thank you so much.
Thank you very much. Take care, Tim.
Yeah.
Bye.
Take care. Cheers, Matt. Thanks.